Assalamualaikum warahmatullah and a very good day to all students. So before I start the lecture today, let me congratulate you for this 50 years anniversary celebration for UPM. Okay, so UPM has started since 1971 and this is already 2021, and our program, which is agricultural engineering program, is one of the earliest programs that was introduced in the university. At that time, the university was known as College Pertanian Malaya. Okay, so congratulations for being part of UPM. Okay, let's start the topic today. So the topic today is flow determination in open channel. So we are still focusing on uniform flow. So what is uniform flow? As you can see from this figure, uniform flow is when you have a type of flow which is stable and which is calm flow. Okay, in this case you can see how uniform flow and how non-uniform flow look like. Okay, and then this is the upstream and this is downstream. So this uniform flow and non-uniform flow can happen anywhere. Okay, so for example, in this example, uniform flow is on the upper stream of the river, so where the flow is uniform here, and then here after the hydraulic jump, then this is where non-uniform flow might occur. Okay, so uniform flow, this already has been discussed in my previous video, where you know that uniform flow happen when you have the driving force is equals to the drag force. Okay, so please watch my previous video about this. And from this situation is where Chizzy's equation is derived. Okay, so from Chizzy's equation, we also learn about Manning's equation. And Manning's equation is widely used to calculate flow rate. Okay, so in this case, flow rate, the equation is still the same. Q is equals to AV. Okay, so when Q is equals to AV. A is the area and V is the velocity. In this case, to calculate flow rate in open channel flow, Q is equals to AV and V is either from Chazzy's equation or it can be also from Manning's equation. Okay, so Manning's, this is the formula for calculating Manning's equation. And N is the coefficient of Manning's coefficient. Okay, R is hydraulic radius, which is A divided by P, and SF is friction slope, or some books call it as energy slope. Okay, so you have to know this. Okay, so Q is equals to AV. This is from Manning's equation. Okay, so K is 1 if velocity is reported in ms, meter per second. So always in our case, K is equals to 1, and then you can use this equation where K is already 1, so it's not appear in the equation. Okay, so this description can be found in chapter 4 of the textbook that I introduced you. Okay, so besides Chazzy's and Manning's equation, there is also another one equation that can be used to describe flow resistance in the open channel. So the equation is Darcy, Weisbach, and Colebrook-White's equations. Okay, so in this equation, okay, so this is taken from chapter 8 from another textbook. Okay, so I will share with you this textbook and you can read from chapter 8. So in the introduction part, the the fact that is presented here is more or less the same with the book that I shared with you earlier. Okay, so you can read it. And then what is interesting in this section 8.2, it describes here, the nature of the boundary resistance is identical to that of full pipe flow in chapter 4 of this book. And the Darcy-Weisbach and Colebrook-White equations for non-circular sections may be applied, okay, in steady flow in open channel. Okay, note that the energy gradient SF is equal to the bed slope SO in uniform flow. So this is the equation of Darcy-Weisbach, and from Colebrook-White equation in chapter 4. Okay, so let's see. Okay, eliminating the unit weight of water, I think this is gamma from equation 8.2 and 8.3. So we have this equation. So this equation is the same like Manning's, where R is equals to A over P, and in this case we have mu. So this is kinematic viscosity, like we already used in open channel in pipe flow. Kinematic viscosity. Okay, also this is temperature dependent, and also it is liquid type dependent. So if we deal with water or oil, then you have to know. So because oil and water have different characteristics, so you have to know what kind of fluids you are working with. So of course in open channel flow we always deals with water. Okay. Okay, so if you want to use Darcy-Weisbach equation, then the formula is like this. You just multiply the Darcy-Weisbach equation and then multiply with A, and then don't forget this negative sign in front of this equation. Don't forget it. Don't forget about it. Okay, so we will learn how to use this equation from the example that I will share with you later. Okay, so normally we only deals with rectangular channel. So rectangular channel is straightforward, quite straightforward. Oh, sorry. Okay, so this rectangular channel, you know that this is Y. Okay, so you know that the depth of the channel is Y, and the width of the channel is B. So area of the channel is equals to Y multiplied by B. Okay, so it's a cross-sectional area of the flow. Okay, so P is wetted parameter. So wetted parameter is taken as this Y plus B plus another Y. So it's equals to 2Y plus B. And R, which can be found in Manning's and also in Darcy-Weisbach equation, and also in Chassis equation, R is equals to A over P. Okay, so this is rectangular channel. How about if you have other shape of channel like trapezoidal in this case, and we can also have semi-cellular or triangular channel. So the formula is here. You can use this formula to calculate the area, the wetted parameter, and also hydraulic radius, of course, and also the top width of the channel. Okay, so you can memorize this equation. Okay, let's see. For example, if we have this trapezoidal channel, so A is equals to B plus NY, and all this part is multiplied by Y. Okay, so N is actually the according to the shape of the rectangular, trapezoidal slope. at these sites. Okay, this will be given either in, yeah, we can see that we can do this in the from the example that I will show you later. Okay, so since the formula is given here straightforward, you can memorize them. And but normally in exams we will give you this, and if it's not given, then you have to memorize this equation. Okay. Okay, so this is a picture of rectangular channel. So this kind of channel, if you are familiar, this is actually very widely used in our country, where, for example, in Tanjung Karang irrigation scheme. So you can see this irrigation channel where the water is supplied to the paddy. And this is an example from, not from our country, but this is trapezoidal channel. Okay, I took these pictures from this website, so you can read them also from this website. Okay, so we are going to do maybe 2 examples, but I will continue on this example in my next video. So see you later. Bye.